My name's Jonathan Gallimore. I work for a company called Tommy Tribe. If you haven't come across us before, we work with a product called Apache Tommy, which you might have come across, which is an app server that's grown out of Tomcat. And we work with a number of customers, helping them to roll out Tommy. And they usually like to throw some hard questions at us. And so this talk came out of some work that we did with a big client of ours a couple of years ago, where we had rolled out Tommy across their estate, and they were like, that's great, it works fantastic. Now what? How do we secure it? And being app server guys, we were sort of thinking, oh, basic auth? But that's probably not really going to cut it. So we went away and looked at various different security specifications and looked at how we can best advise them. One of the things about security specifications is there's so many of them to choose from, and one of the things that we found is that it's a huge minefield. So, if you've ever tried to read one of these specifications, they tend to assume quite a lot of previous knowledge, and often they reference dozens of other specifications. So you can very easily sort of read through a spec and then find 20 references at the end, and so then right, okay, I've got to go off and read all of these, and then when you're reading that, you've then got another set of references to follow, and then suddenly you find you're sort of right the way back at the beginning, and you've done a full loop. So what I'm going to do in this talk is just talk about a couple of different things that we've looked at on our journey. So we're going to take a look at sort of where we are with basic auth. Look at Oauth, and then we're going to build on top of that using JSON web tokens. I'm also going to talk about a little specification called HTTP signatures. But what I'll try and do throughout all of that, I'll try and keep it real simple, but also show how that relates to our architecture and how small changes that we make within our security layer can have some big impacts within the architecture of our application. So the baseline architecture that I'm going to talk about looks a bit like this. So hopefully this looks a little bit familiar to everyone in the room. So our application, we've got 1,000 users, each of which are making, they're doing 3 operations per second to kind of the front door of our application. And then for each of those operations, we've got some microservices sat behind. So for each operation, we've got 4 microservices that we're going to call to collect information to return back to the user. So if we take a look at basic auth and how it sort of sits in this architecture. Okay, so for anyone who's not familiar, this is what a basic auth message might look like. So we're doing a fairly straightforward post to a service here, and for every call that we're making through to the service, we're adding this authorization header with a basic scheme. And then this thing here, this is super secure. I'm just kidding. It's this is the username and password appended with a colon in the middle and base64 encoded. So it's worked for dozens of years, but if you pick this up on the wire, it's pretty easy to decrypt it and figure out what the credentials are. So in our architecture, if we're sending the username and password base64 encoded for every call that these clients are making, then effectively, we're doing 3,000 transactions per second against our front end, and then we're then presumably validating the username and password there, and we might be using something like LDAP or a user database to that. So we actually have 3,000 transactions per second going against our LDAP system. So that gives us a kind of a scalability issue there. So on the back end here, I've got no authentication. Are people passing authentication to their back end services? Quick show of hands. Okay, a few. So any of those are you passing basic authentication, or are you doing something different? Got someone nodding at the front, I think. So if we get brave and send the username and password through all the services at the back end, they're all going to validate those credentials as well. So now we have 12,000 TPS going against our LDAP server in the back end, so we've got 15,000 TPS in total. So this isn't a particularly, this doesn't scale particularly well. We do see a lot of people doing whitelisting. So, you know, people are saying, you know, we trust the servers that we've got on the front end, so we're not going to require any authentication to be passed through. In that sort of scenario, what we end up with is a bit of an elasticity problem. So if we want, you know, if we decide that we want to add some more servers in here in order to scale these up to handle more volume, then we've got to go and continuously modify our whitelist. So it doesn't fit into an elastic structure where we want to spin up and shut off nodes as and when we want to. We have one other problem where we're not passing authentication through, which is how these microservices communicate to each other. So here we've got microservice A making a request to microservice D saying, hey, can I have all of Joe's salary information? Microservice D is saying, hey, well, I don't know who you are or why you want Joe's salary information, but sure thing, you know, here you go, take it. You know, and in this scenario, we're kind of getting a possibility that, you know, someone can actually talk to microservice D and scrape large volumes of data because we're not actually checking that it's Joe who's kind of on the front end of this request. Okay. So we've got another scenario just to play through the architecture. So we've got Latveria Attacks. Anyone know where Latveria is? Okay, it's where Dr. Doom is from. Can't actually use a real country. So Dr. Doom and his minions are sending a very large number of malicious requests through our system. So we've got the 3,000 TPS that are valid requests from our 1,000 users, and we've got 6,000 TPS where we're effectively getting lots of bad traffic. So we've now got 9,000 TPS going through our LDAP server. So effectively, there's a possibility that our LDAP system is actually being DDoSed by these malicious requests. So one way that we can change our architecture is we can look at Oauth 2. So is anyone using Oauth 2 at the moment? Can I get a show of hands? Okay, we've got a few. So if we put Oauth 2 in here and take a look at how that works and how it looks in our architecture. So the first thing with Oauth 2 is that what we do is we issue each user's device with a token. Okay, so rather than each device sending over a username and password, we issue a token, and they send a token over with every request. This has a great advantage that if you lose, say, your phone or your tablet, you're able to go and revoke those tokens individually. So, you know, if I lose my tablet, I can go into the system, I can revoke that token, and that device will no longer be able to access the application. But my phone and my laptop will carry on working as normal. In terms of how Oauth works, there are a number of different flows, and I'm showing what's called the password grant here. So when the user logs into their application, they send a request, a post request to a token endpoint, and they provide various details in their URL form encoded. Okay, so we've got a grant type of password, and we've got Snoopy's username and password going there. And then what happens is the gateway will go off to LDAP and verify that password, and then it will generate a token, and it will store that token along with some of your details, such as what roles you might have in the token store, and then it will return back a JSON payload that's got an access token and a refresh token. And you can see there's also, that might be a little bit small at the back, but there's an expiry time here. So on this slide, it's set to expire in an hour's time. And so when you actually make a REST call using Oauth, the call looks a little bit like this. So we're actually making the same call here, but instead of sending basic authentication on our authorization header, our scheme is set to bearer, and then we provide the access token that we were given in the call to the token endpoint. And we can keep doing that over and over again. So we can call various different services, and eventually we'll get a 401. Okay, so when this happens, our access token has expired, and we'll need to go back to the token endpoint and get a new one. Okay, so we do this using the refresh token. So the refresh grant works in a similar way. Okay, so we call the token endpoint again, but instead of passing the username and password, we send through the refresh token, and we get a new access token and refresh token pair. Okay, so there's our old pair and our new pair. So if we continue to try and use the access token, we're going to continue getting 401 responses. So we'll substitute in the new one instead. Now, it's worth pointing out at this point that the use of the access token and the refresh token isn't necessarily, there aren't strict rules around that. So we have seen implementations of this where the access token can live forever, and that can give you a situation where if the access token is stolen, much like your password, the person who's got that can effectively log into the system as you and impersonate you forever until that token is revoked. The other thing that we've seen is the possibility that refresh tokens can be used multiple times. So if your refresh token is somehow intercepted, then not only can the person who intercepts it impersonate you, but they can actually use that to create more access tokens. So it's almost like you've been impersonated and then cloned as well. So it's just worth checking how that works. So if you have an OAuth 2 vendor, it's worth understanding how the access tokens and refresh tokens are issued and how their lifetime works. So in all of this, what have we achieved? We've got more passwords, or at least our devices have. So all of our devices now have this access token, and we have to keep track of all of these access tokens. We've also got a few new terms that we have to deal with as developers. So the first term is we have a password grant. Okay, so calling that token endpoint and getting the JSON payload back. That's called the grant process. And does that look familiar to anyone in the room? Maybe those of you who aren't doing Auth 2 already. To me, we're passing through a URL encoded username and password and getting something back. So it looks very much like a regular login screen that we've all been creating for years, but it's just got a new name. Okay. And we've got the concept of tokens, which, as it is here, is a slightly less crappy password, but we like to think of it as an equally crappy HTTP session ID. So you're logging in, providing your username and password, and you're getting back just a short unique string. So it works very much like a HTTP session. Okay. So if we take a look at this in our architecture, okay, we're making a few assumptions here. So the first assumption that we've got is that we're going to ask our users to log in every day, and we're going to issue a new access token to them. So right at the very top, we've got 1,000 requests coming in to do our actual login, and they're going to be validated against LDAP. And then that access token is then going to be used for all of the calls during the day. So we've got our 3000 TPS coming in with our bearer scheme on our authorization header. And as a result, we're going to go off to our token database down at the bottom. And we're going to have 3000 TPS of token checks against that database. And then on our back end, we're still using IP whitelisting, so there's no additional traffic there, but also we're not gaining any benefit at the moment because we're not doing anything with those tokens. Okay, if we then start actually propagating the authorization header through to the services on the back end, we end up with a slightly different problem. Okay, so we're going to pass through the token through to our back-end services. We're going to say, it's going to say, who the heck is this? I've no idea. Go and ask the token server. So if you actually want to check on the back end who this token belongs to and whether they actually have permission to call the service or not, the back-end service actually needs to make a call to an introspect endpoint on your token server. And so what we actually end up with is 8 hops on our back end and 12,000 TPS in addition to our 3,000 TPS at our token server. So we hope that this thing doesn't catch fire or stop working altogether. So what we effectively have here is all of our state around our user and our roles and the metadata there is all being held inside a database, inside our token server. And both the microservices on the back and the clients on the front each get a pointer to this state. So wherever we go, we have to use that pointer and go and look up that state in the database. So our access token, is it really an access pointer or maybe even an access primary key? I think token is probably a term that sells better from a marketing perspective, but effectively it is a bit like a primary key to go and do a lookup to retrieve this information. And our Oauth 2 is really a bit like a high-frequency password exchange algorithm at this point. We're continually sending in these tokens and then swapping them out when we refresh. So we'll take a look at a way that we can change this around and make a relatively small change, but get a big impact. But just as a slight aside, we get a little bit of feedback. So we have how would we go about solving this problem? Does anybody want to throw out some ideas? Hashing? Yeah, excellent. So we can take a checksum or a hash of the file and do a comparison. So when you download something, you'll maybe go and check a checksum or a hash to verify that what you downloaded is actually the file that it claims to be. So we'll just take a quick look at hashing and how that works. Okay. So just very simple. So if you're not familiar with hashing, you can kind of think of it as, in effect, we're creating a statistically unique number that represents the data. Okay, so I've got a little bit of an analogy here. If you imagine a snow globe and it's full of bits, and as we run data through it, the snow globe shakes, and then once that's done, we're going to crack it open and take the bits out of the snow globe. These bits down here are effectively our hash. So the important property here is that if we run the same data through, we should get the same hash. So if we go and get a hash of a file, and we do that over and over and over again, each time we should get the same hash. If we put different data through, then we should always get a different hash coming out. So more bits are better. So more bits enables us to use bigger numbers, and we get a better chance of getting a statistically unique number with less chance of hitting duplicates through this process. Okay. If the snow globe analogy doesn't quite work for you, you can think of it as playing some music as the data's going through. The keys are being toggled, so the keys represent the bits of the hash, so they're being toggled 1 and 0, and then what you would end up there would be the hash. So I will just show you an example of hashing. So I'm not a big follower of football, but I gather that there is a big football tournament going on at the moment. So I took some data and I ran it through my hash program. So I've got Portugal 3, Spain 3 here, and I've hashed that with various algorithms there. So, you know, if you kind of imagine that at the end of the game, the referee, you know, creates a hash of the score. You know, even if we tried to say, you know, Portugal 4, Spain 3, you'll notice that the hash values are completely different. So if we go and validate that against what, you know, the hash that the referee says it is, then we know that data has changed. Okay. Now, obviously, we can create hashes, but there's nothing to stop people sort of tampering with those. If you change the data, you can just generate a new hash from that data. So we can look at some different ways of protecting the hash. And so typically, we would do this by encrypting or signing the hash. And we can do that using either a symmetric key. So this is one where you would use the same key to effectively lock and unlock the box, or you can use a public-private key pair. And so the idea here is that the referee would have the private key, so they would create their hash and sign it using the private key, and then everyone who wanted to verify that hash would have the public key. So they can't actually, you know, they can't actually create a new hash because they don't have the private key, but they can go and verify that the one that they've been given is correct. And we can encode these hashes or signatures in various different ways. So typically we would use base 64. Apparently there's a base 85. Has anybody ever come across that before? Nope. Nope. Me neither. But apparently it's a thing. Let's have a look at how we can use this alongside Oauth 2. So there, we can use a technology called Json Web Tokens in conjunction with Oauth 2. We can use that to get a really big architectural impact. So the way Json Web Tokens works is basically it's a fancy JSON map. So there are some standard key pair values that are defined by the specification to put in. These would be things like who it's issued to, when it was issued at, when it will expire. So the expiration is completely built into this. Once that JSON map has been put together, we base 64 encode the whole thing, and then we sign it using either an RSA key or a HMAC key. Just one note, it's pronounced jot. I have no idea why. I don't know when the W became an O, but if you hear people talking about jots, this is the thing that they're talking about. So previously, our access token looked a bit like this, just a random, fairly short random jumble of letters and numbers. And with JSON Web Tokens, our access token looks a bit like this. So it's kind of important to understand the breakdown of this, because otherwise you'd be kind of tempted to say, well, actually, I think the short version is better, right? So there are three parts of the token. Okay, so there's the header, the body, and then there's the signature at the end. So they're highlighted in three different colors there, and they're each base 64 encoded, and they're separated by the dots. Okay. So the header that we've got at the top in purple is basically explaining how the token was assembled and what algorithm was used to sign it. And then the bulk of the stuff is in yellow in the middle, and I hope you can see it okay at the back, but I'll kind of read out what's there. So we've got the username. So we've got Snoopy here. We've got the kind of animal that he is. And then we've got this scopes bit in the middle. So scopes are a bit like roles. Okay, so we can see here that Snoopy's got access to Twitter so that he can tweet to his millions of followers. And then finally at the bottom there are these sort of standard key value pairs that I mentioned. So EXP is the expiration date of the token, so that's just as a timestamp. IAT is the issued at date of the token, and then JTI is a token identifier. So this is just a unique identifier that the server can keep hold of in order to keep track of these things for revoking tokens and so forth. So, and then at the very end is this is the hash that's been encoded with our key. Okay, so this is the signature part at the end. So this is a very high impact change from an architectural point of view. But in terms of how we actually use the token, it's very, very similar. So just to sort of recap what we had. So we were doing our password grant. We were pulling user information from LDAP, generating an access token pointer, inserting all of this information into a database and sending back the pointer to the client. Okay, so we have our state on the server and we have our pointer on the client. With the JSON Web Tokens world, we again do our password grant, we pull the user information from LDAP, we format that data as a JSON map, key value pairs, we sign that with the private key, we put just the pointer into the database, and we send the whole thing back to the client. So now we've flipped everything around. So the server is holding a pointer, and the client is holding the state. And so effectively, this is a little bit like where we had a HTTP session ID before from our login. This is now a bit more like HTTP cookies, where we're sending the state back to the client. Okay. From a password grant perspective, it works pretty much the same way as it did before. So we're calling the token endpoint at the top, and we're getting our JSON payload at the bottom with our access token and refresh token and expiry. But at the back end, that's the bit that's different, where we're actually generating the token. In terms of actually using the token, that works in exactly the same way. So we're just passing the full JSON Web Tokens token with the bearer scheme on the authorization header. Okay, so it actually works, in terms of the interaction between the client and the gateway, it works in exactly the same way. So if we take a look at this in our architecture, you can see that things are a little bit different now. So we have our 1,000 usernames and passwords sent at the top to authenticate our users at the start of the day. Then we have our 3,000 TPS regular calls, but slightly differently now, we have decided to do a check just on the refresh token here. So this is a trick that you can do. You can have quite a short expiration time on your access token and do the check at the database on the identifier for the refresh token. Okay, so you would actually revoke the refresh token rather than the access token. But because all of our token validation is done just in memory and CPU, we can do that right here on the gateway. We don't actually have to go anywhere we don't have to make any calls in order to validate this data. We can do that purely with the public key and say, is this valid? And then check the various values inside the job to say, has it expired? Was it issued by the right place, signed with the right key, and so forth. Now on the back end, so if we're still, if we're not propagating the token through, we can say, hey, you didn't pass a token. So when you say, hey, give me all of Joe's salary information, not a chance, no way. If we pass the token through, and each one of these microservices has the public key, they are also able to validate and check that token using just memory and CPU to check that and not have to go off and call anything. And so they can actually check the token and ensure that the data that's being asked for actually originated with the person who's asking for it. So, can you give me all of Joe's information? Well, if it's Joe's token that was passed through, then yes, absolutely. So this kind of prevents this scenario where we might be scraping large amounts of data by making direct calls to the microservices on the back end. So these guys are back. They've decided to, it's nighttime for us and daytime for them, so they've decided to have another go. And this time they're taking a guess at trying to brute force tokens against our gateway. So we have our 3,000 TPS of good traffic from our users here, and another 6,000 TPS of invalid tokens. So the good news here is that we're not sending these 6,000 TPS through to our LDAP system. They're getting dropped right at the gateway. They're not passing validation with our public key because they weren't created and signed using our private key. So they're just ending up straight on the floor at that point. So that traffic isn't making it through. And because we're doing all of this with just RAM and CPU, if we need to scale out our gateway, we can just add more machines here. It's a fairly stateless architecture, so we're able to just throw more machine power at it. So what we've achieved here is just making the change to using JSON web tokens. It hasn't impacted how the gateway and the client interact with each other, but it has had a significant impact in terms of, alleviating the pressure on things like our LDAP or our identity provider there. So I would encourage you, if you're doing Oauth, and talk to your vendors and see exactly how things work and whether they're using JSON web tokens or whether you would be incurring lots of calls through to the database. So I'll just move on and I'll talk about HTTP signatures. I don't know if anyone's come across this before. Does anybody use Amazon EC2? Okay, a good few people. So when you create a request on Amazon EC2 to spin up lots of machines, they require you to sign every request that you make to them. So when you sign up for an account, they give you a key ID and they give you a secret key, and you have to use those credentials each time to actually sign the message. And the idea here is that if you spin up 1,000 machines and then forget about them and rack up a huge bill, you can't go back to them and say, well, I only ordered 10 machines. I don't know what the other 990 are all about. Because they can say, well, you made that request and you signed that request using your key. And so we did have a chat with Amazon, because their API, if you take a look on GitHub, it's all there and open source. And we sort of said, hey, do you mind if we use that? And they pointed us at the HTTP signatures specification. So I'll show you a little bit about how that works at a request level. So the key thing here is that at no point does a secret get transmitted between the client and the server. What we actually do is sign the message itself, and that requires effectively the client to continually prove to the server that it possesses the key, but without ever actually handing over the key. And we can use this to both prove identity and also prevent messages from being tampered. There's a link to the spec there, and I'll make the slides available. I'll put these on Twitter at the end of the talk. This spec is well worth having a look at. It's about 20 pages long. There are tons of examples in here. It doesn't go off and refer to dozens of other specifications. You can read it and get a really good feel for to use it and how to create an implementation against it. And you could most likely implement this in a day. So the first time I had a go, I think it was maybe just a little bit more than a day. I recently had a go at implementing it in C using OpenSSL, and I haven't done any C programming for about 7 years, and I've never used OpenSSL for anything at that level. And I was able to get it going in a couple of hours. So it really is straightforward and easy to get going with. So a typical message looks a little bit like this. Okay, so there's no call to there's no call to a token endpoint or anything like that, or passing through any credentials to get a key. We are just sending over an authorization header with a key ID, an algorithm, and some headers and the signature. So each of these components, so the key ID, as you might imagine, says I'm signing this request using this particular key. There are a few different algorithms, so you can use RSA with this. We typically use the HMAC SHA-256, but it works perfectly fine with the public-private keys as well. The client is then choosing a number of headers in the message to form the signature. And then the signature that is here is computed by putting those headers together and then signing it using that key. So the way that the signature is actually created is we create a signing string from the specified headers. So they are just key value pairs, and they're concatenated together just using a new line. So we've got the \n at the end of each of these. The request target is a virtual header that's defined by the specification, which is just the verb, the HTTP verb, and the context path. So it doesn't include the host name. You can sign the host name. You can sign the host header separately if you want to. And then we just then sign that string and base64 encode it to get that signature. One of the key things here is that the client is choosing what to sign and not the server. But the server does have the opportunity to sort of veto all of this information. So the server can come back and say, actually, you didn't sign these headers that I expected to be included in the signature, so your request isn't valid. So one thing that you will likely want to do is choose a piece of data to sign that changes each time. So you should probably include the date as something that you sign in every request, and also validate on the server side that the date is actually not in the past. So because where you would typically steal a token in the Oauth 2 scenario, the message here would be the thing that you would actually steal and try and replay. You might be thinking, is it possible to protect the body of the message? And the good news is that you can. The way that you would do that is there's a specification where you can create a hash or a digest of the body using a particular hashing algorithm, and then you can then just add a digest header onto the message with that hash, and then you would then include that digest header inside your signature, and then you would obviously need to verify the digest when you get the message on the server side to make sure the hash there actually lines up with what's actually in the request body, and that hasn't been tampered with. Okay. So our architecture with HTTP signatures is a little bit different. So we're not sending any passwords across. We will be hitting most likely a key store to go and pick up the keys that the messages are signed with, and how much traffic you have there will really depend on how many keys you're using and how you maintain and rotate those. This issue is a bit interesting. So what would typically happen is that you would have a key that two servers would agree on, So, we can verify that the message was signed using microservice A's key at microservice D, but we're not identifying that Joe is the caller. So we know that we can trust this as a caller, but we don't know that it was necessarily Joe on the other end who was asking for for the information. And so this doesn't replace Oauth 2 and JSON Web Token, so you wouldn't necessarily choose to use one or the other exclusively. You'd most likely want to try and put them together somehow. So there are a few ways that you can do that. So you can just agree on keys between your gateway and your microservices and distribute that, and then use Oauth 2 on top of that. But there is some new stuff that's going on in the Oauth 2 world. So there's a specification called proof of possession, and this basically provides a way of distributing keys for HTTP signatures when you actually log in to get an access token. Okay, so in effect, what this specifies is, so here's our access token before. With proof of possession, when you make the call, you actually get handed back a key ID in the access token, and in the body of the request here, you actually get the key to use for the signature itself. So there is a little bit of a weakness there in that the key is actually being sent over the wire and not through a different communication mechanism. But it's only sent the once, and then the client will need to continuously prove that it has that key by signing every message it sends using that key, and also providing the access token as well in order to provide the user information over to the services. So this is fairly new. So again, it's worth, if you're talking to a vendor for Oauth 2, it's worth seeing what they offer in this regard. So, and this is how a request where you're using both an Oauth 2 JOT and HTTP signatures together would look like. So you've got one authorization header here, and you're providing both the signature and the bearer token in one. So this header's getting a little bit complicated, but you've basically got two authorization schemes going on here. Okay. So just coming back to our architecture here. We've basically got our passwords being sent daily again with 1,000 requests at the top. We've got our 3,000 TPS and our signature verification going on at the database. Our refresh token traffic is fairly minimal, and we're validating everything with signatures all the way through. So there's the reference for the specification. I am almost out of time, but just some takeaways from the talk. If some of this is a little bit confusing, if you understand hashing and signing and protecting those hashes using keys, then you're pretty good. But in effect, if you're using Oauth 2, do consider using JSON Web Tokens, as this can drastically change your architecture and reduce the load on your IDP system. And plain Oauth 2 is effectively like HTTP sessions, and Oauth 2 with JSON Web Tokens is much more like HTTP cookies. Okay. One last thing we did. We did sort of take what we learned and built it into a security product. So if you are interested in that at all, feel free to come and have a chat with me, or you can check out the website on the screen now. So So I think we've got a few minutes for some questions.
In HTTP signatures, could you just add the bearer token as a part of the signature and just leave JWT without signature?
So I think that's a really great question. I think what's tricky there is, in effect, the way that it works is that the client computes the signature, and then the server does the same computation. So yeah, I mean, so if you included it as a separate header, then in theory, yes, you could sign the token as part of that and have that signature checked on the other side as well. That would in theory work just fine.
Any more questions? All right.